Hello, we meet again. Okay, so we are going to continue with part 2 of lecture 16. We're going to proceed with understanding the Bode plot for a real pole. Okay, so real pole, the equations for the real pole, yeah, is Hs equals to 1 over S over P plus 1. Okay, right, and in J omega terms, we're going to have Hj omega of 1 over 1 plus j omega divided by p. Okay, so in terms of the amplitude, when we write this as j omega in terms of dB, we can prove that the amplitude in dB can be written to be negative 20 log of the modulus of the amplitude of 1 plus j omega divided by p. And on the phase angle, okay, it can be proved that the angle for this will be a negative arctangent of omega divided by p. Okay, I hope that you can prove on this amplitude and phase angle on your own. Yeah, so if you face any problem with this proving, yeah, so you can just consult me on this. Yeah, but I hope that you have learned about this method of calculating the amplitude and also the angle when we face a complex number condition. Yeah. Okay, so in terms of the amplitude plot and the phase plot, so these are the rules that need to be taken care of. Yeah, there are two phases that need to be considered for the case of amplitude plot. The first case, yeah, for the amplitude plot is for a lower frequency where omega is much lower than the pole value. Yeah, omega is much lower than the pole value, so the amplitude will be 0 and the phase angle will be 0. It can be proved from this equation and from these two equations. Yeah. So imagine that when omega is smaller, much smaller as compared to p, so we can assume that j omega divided by p will be 0, left only with 20 log of 1, and this will lead to 0 value of dB. And also if omega is much lower than p, so we can say that omega divided by p, the ratio of these will relatively equal to 0. So arctangent of 0 is 0. That's why we have for the first condition where the lower frequency case, amplitude will be 0 and phase angle will be 0. Okay, and for the higher frequency where omega is much bigger than p, so it can be noted that for the amplitude plot, we can ignore the value of 1. Yeah, because omega is much bigger than p, so we can only consider the existence of these terms of j omega divided by p. So that's why for the amplitude, it can be written that the amplitude will be negative 20 log omega divided by p. Whereas for the phase angle, when omega is much bigger than p, this value will be approaching infinite. Yeah. So negative arctangent of infinite will be negative 90 degrees. Okay. So these are the two conditions that need to be taken care of when we sketch the Bode diagram for a real pole case. Yeah. Okay. All right. And for the amplitude plot, the intersection between the lower frequency and the higher frequency is what we call as the corner frequency, which is the location of the pole value. Okay. Whereas for the phase plot, the slope between the lower frequency and higher frequency is negative 45 degrees per decade. Yeah. Okay. The slope between low frequency and high frequency is negative 45 degrees per decade, and at corner frequency the angle is negative 45 degrees. So I'm going to show you after this what's meant by this sentence here. Okay. Okay, so let's have a look at the diagram, the sketch for this real pole case. Yeah, so this is the sketch for the amplitude. Okay, so the amplitude, it is said just now that for lower frequency case, the amplitude is 0 in dB. Okay, and for higher amplitude, for higher frequency case, the slope of the graph will be negative 20 dB per decade. Yeah, where the amplitude is given by negative 20 log omega divided by p. Okay, so this is a typical plot for the case of real pole, where the corner frequency is located at the pole value. Okay, so this is the condition, the sketch of the amplitude for a real pole. Whereas for the phase plot, for the phase plot, you see that for lower frequency, the angle is 0 degrees. For the case of higher frequencies, the angle is negative 90. And at the pole value, the angle is negative 45 degrees. So it can be noted that for one decade lower, so we have P here, the pole value. So one decade lower, which is at 0.1 P, the angle will be 0 degrees. And for one decade higher, which is at 10 P, the angle will be negative 90 degrees. So if we connect this point at 0.1 P, negative 45 degrees at P, and negative 90 degrees at 10 of P, we're going to have a slope of the phase plot of negative 45 degrees per decade. Okay, so this is a typical plot for the phase if we are having a real pole case. Yeah. Okay. So again, I repeat. When we have a real pole case, your amplitude plot will be look like this: 0 dB until the pole value, and then we are going to have a slope of negative 20 dB per decade for a value of frequency higher than the pole value. Whereas for the phase plot, we are going to have 0 degrees for a frequency of 1 decade smaller than the pole value. And we are going to have a phase of negative 90 degrees for 1 decade higher than the pole value. And knowing that at the pole value, there is a phase of negative 45 degrees. So when we connect those points, we are going to have a slope of negative 45 degrees per decade. Okay, right. Next will be a real zero case. Yeah, a real zero case. For a real zero case, we are going to have the HS is 1 plus S divided by Z. Okay. In J omega terms, we're going to have H of J omega of 1 plus J omega divided by Z. Okay, so from here, we can write that the amplitude in dB can be written as 20 log of 1 plus J omega over Z, and the phase angle will be simply arctangent of omega divided by Z. Okay, again, we have to divide into two conditions for the phase and amplitude plot. Same like what we did for the real pole case in the previous slide. Yeah, so for lower frequency, omega much smaller than Z, so the amplitude will be 0 and the phase angle will be 0, which is evidently shown by these two equations. You can prove this on your own. And for higher frequency case, where omega is much bigger than Z, the amplitude in dB will be 20 log omega divided by Z, where we ignore the effect of 1. Okay, and remember that for the case of real zeros, for higher frequency, there should be a slope of 20 dB per decade. And based on the phase angle equation, and based on the conditions of omega is much bigger than Z, the phase angle will be then equals to 90 degrees. Okay. So at the for the amplitude plot, the intersection between the lower frequency and higher frequency plot is the corner frequency of Z. Okay, and for the phase plot, there should be a slope between lower frequency and higher frequency of 45 degrees per decade, and there should be an angle of 45 degrees at the corner frequency value. So let's have a look at the sketch for the real zero. Okay, so this is the sketch for the real zero, which is against what that we have seen just now for the case of real pole. Yeah. So for the case of real zeros, for frequency lower than Z, the amplitude will be 0 dB. For the case of frequency higher than Z, Z is a real zero value. Yeah. For higher frequency of Z, there should be a slope of positive 20 dB per decade. Okay, and related to the phase angle, again, for the case of 1 decade smaller than the Z, or the zero value, 1 decade smaller, which is at 0.1 Z, the phase is 0 degrees. And for higher frequency, which is 1 decade higher, which is at 10 Z, the phase is positive 90 degrees. And knowing that at the at the zero value Z, the angle is 45 degrees positive. So there should be a slope of positive 45 degrees per decade between 0.1 Z, Z and 10 of Z. Okay, so this is the plot or sketch for the real zeros conditions. Yeah. So up to now we have learned about 5 different plots. The first plot is for the constant. So if you permit me to recall back the plot. So this is a plot for the constant. Constant dB, constant amplitude, 0 degrees of phase. For the pole at the origin, a slope of negative 20 dB per decade, passing through 1 at the frequency, and phase constant of negative 90 degrees. For the zeros at origin, there should be a slope of positive 20 dB per decade, passing through 1 at the frequency, and constant phase of 90 degrees. And this is the plot for the real pole, as mentioned just now. And this should be the plot for the real zeros. Yeah. Okay. So we have understood that these are 5 cases that is allowable, or that is available in the transfer function: constant, zeros at origin, pole at origin, real zeros, and real pole. Yeah. Okay. So let us proceed now. Once you have understood that these are the available plots for different component of the transfer function. So how to obtain the actual transfer function for how to obtain the actual plot for the transfer function. Okay, let's have a look at this transfer function. We have Hs of 100, s plus 1 divided by s plus 10 over s plus 100. Okay, so what you have to do when you are facing this problem is that always write, the first step is always write the Hs in the correct form. Okay, the correct form should be look like this, where we have 100 over there, that's constant, should be there. We have 1 plus s. So all the condition, all the terms, let's say for example, you have s plus 10. So what we have to do is that we have to take out the 10 outside, like this. We have to take out the 10 outside, and we have to write it as 1 plus s over 10. The same things happen for the s plus 100. We have to take out 100. Yeah, we have to take out 100, and we're going to have 1 plus s over 100. And the constants now will become a new value, which is 100 divided by 1000. So we're going to have 0.1, and the rest will follow. So 1 plus s over 1 plus s over 10, and 1 plus s over 100. Okay, so this is the first step. You need to write the Hs in the correct form. Yeah. Okay. So number 2, we have to do is that you have to obtain the magnitude and the phase plot for all the terms that you have in the transfer function. So if you base on these transfer functions here, we have 4 different plots. Yeah. We have a plot for the constant of 0.1. We have a plot for real zero. Yeah, real zero at 1. We have real pole at 10. We have real pole at 100. So there should be 4 different plots that can be sketched. Yeah, I repeat again. These 4 different plots are a constant at 0.1, a real pole, real zero at 1, real pole at 10, and real pole at 100. So these are the plots that can be obtained from the Hs. And once you obtain the plots, both magnitudes and phases for this transfer function, you are going to head to the third step, which is the plots in number 2 here can simply be added. So what we have to do now is that we have to add them together. Yeah. So we have to add them together to obtain the actual magnitude and phase plot for the Hs. So these are the steps that need to be taken for the Bode sketching. Yeah. Number 1, have to write the Hs in the correct form as shown in the equations here. Number two, you have to obtain the individual plots for every terms in your transfer function, both the amplitude and the phase. And finally, you have to add them together to obtain the final plot for both magnitude and phase. Okay, so I'm going to stop now. So you have to understand well on these issues. So afterwards, we are going to do exercises to ensure that you really understand how to sketch or how to obtain the Bode plot for the given transfer functions. Yeah. Okay. Thank you. See you again after this.